Okay, I'm gonna get started here. I'm sure we'll get more people coming in, hopefully. This is one of my favorite things to talk about because it's bizarre and it takes us to something that is more on the cutting edge of what is being found in physics than a lot of the stuff that we talk about. And so this week we're going to talk about particle physics. So we're going to get into the idea that the particles that we talk about as the smallest actually aren't the smallest. And so we're going to kind of move into that and get into some ideas for that this week. So essentially, throughout history, there's always been this idea that we're always trying to figure out, is there something smaller? Is there something bigger? Is there something that we don't know? And how do all these pieces go together? And so we talk a lot throughout just what we do about how do we observe, how do we measure, and how do we then control what we have. And this stuff that we're going to talk about really gets into that observing part. Even more so kind of goes a step before that to this like theorizing and thinking about and taking and like wondering. It's that sort of piece where we're asking questions and saying, well, what else could there be? What else can happen? And how do these things work? And when we talk about this, we're really still sort of hanging in that spot. And particularly for what we're going to discuss, we're very much in that spot. We're just like, what is this? What's happening? And how does it work? And so my goal is to give you enough information to have a general understanding of how protons, neutrons, electrons are structured, how they interact, what these different subatomic particles are, and how they behave. And so some of it is just a little bit, you sort of have to loosen the grips on how much you might normally dive into something and understand something, and kind of let it sit in that uncomfortable spot of what is she even talking about, and working within that and getting that to be an understandable place. So that's the goal. That's what we're doing. And so I'm going to go through a PowerPoint. I'm going to get going on it today. In the way of your practice problems, you'll have a page that I'll put up, and it has all of the terminology. It helps to make connections in what's happening, and it works through some of the different laws that are kind of driving what we know about this. So there's not a lot of problem solving. It's mostly applying the stuff that we have. It's either kind of big picture stuff of how it works, and then how to apply it to what we're doing. And so I have, with what we have right now, today I'll give you some stuff, and when we meet next week on Tuesday, I'll give you some more stuff. And so we'll kind of go through that. I'm not assuming that you'll be able to necessarily finish everything in your practice problems before Tuesday, because I'll be introducing some stuff and going along with that there. And so we'll kind of have to monitor and adjust in what happens. I do have some videos up that walk through the different pieces, and it may be helpful to watch those just to get it in your brain and what we're doing. The thing that's hard to do this virtually is there's so much discussion that we all have just in passing and in figuring out. And so we may adjust on what we need to do after we meet next Tuesday and see how far we get on things. So I'm going to share my screen, and I'm going to pull up the PowerPoint. I'll go like this. And the first thing, it can be a little overwhelming to think about all the different pieces that are happening with this. And so I just want to show you what that idea is looking at and how this goes. So the things that they want you to understand, they want you to understand quarks, leptons, and the antiparticles, hadrons, baryons, and mesons, conservation laws of charge, baryon number, lepton number, and strangeness. There are other ways of conservation. We're going to focus on these four. Nature and range of the strong nuclear force, weak nuclear force, and electromagnetic force. So how those compare to each other and what happens within the process of those. The idea of exchange particles, Feynman diagrams, you'll need to be able to draw and understand, and then the idea of confinement, quark confinement. And so we're going to work through those things. It ends up being, while those words all look ridiculous, oh, that's not what I wanted to hide, sorry. While the words all look kind of goofy, hopefully you'll be able to have them in working order in a little bit. Oh, and then the Higgs boson we'll talk about as well. I need to mute this. There we go. So what should you be able to do? Talk about the Geiger-Marsden experiment. We have talked about that. We'll talk about it a little bit more. That's the gold foil experiment where they were bombarding the gold foil with a neutron or with a proton, sorry, and seeing how it behaved. Applying conservation laws in particle reactions. So the particle reaction will be given to you, and you'll need to be able to work through and determine, based on your conservation laws, if it is a probable reaction that could occur or if it breaks one of the conservation laws and would not be able to occur. Describing protons and neutrons in terms of quarks. So those will be two you'll need to memorize. That'll be it on the memorizing of them. Comparing the interaction strengths of the fundamental forces including gravity. So being able to kind of on a scale of weakest to greatest and general magnitude, be able to discuss the strengths. Describing the mediation of the fundamental forces through the exchange particles. So how the forces occur and what exchange particles drive or are included with that. And then sketching and interpreting simple Feynman diagrams. And that's a drawing that visualizes what happens with the way that these particles interact, and then describing why free quarks are not observed. So the idea of quark confinement. So those are the things that we're looking at. I know it can sound a little bit daunting when you're looking at stuff that's completely new and what happens, just all the different things that go with that. In the way of our data book, you'll have the quarks, you'll have this chart that talks about the quarks. So you don't have to memorize it. You just have to know how to use it. And I'll be explaining on all of those pieces with it. And then you'll have a lepton chart as well. So that will, again, something that you'll need to be able to do and recognize, as well as for the exchange particles that drive the forces. So all of those show up in the data booklet. The very first year I taught SL physics, doing stuff like this was one of the options, and the class was really interested in it. So I'm like, yes, let's do it. But what happened was they didn't have any of these in there, and it was completely ridiculous to actually be able to talk about it. So I'm glad that they have the pieces that they do, and I think it's helpful, and it drives what you're able to do then as well. As we talk about international mindedness and TOK, so international mindedness, when we talk about the idea of this research, it is a really high level research, and it requires a lot of, like, you can't just go and be like, yeah, I'm going to go to the cupboard and get what I need to do this experiment. It requires designing and building and figuring what type of equipment you might need in order to get this research to happen. And so it is definitely an international effort. Think about places like CERN, where you've got scientists from all over the world that are working on that. TOK, oh my goodness. Like you can TOK this all over the place if you want. And so the question that they raise here is, does the belief in the existence of fundamental particles mean that it is justifiable to see physics as being more important than other areas of knowledge? You could argue that all day if you want, that if we can't understand that, then, or if that's not a part of what we have, then everything else doesn't matter. I don't know. You can take that in lots of different ways. And then that just goes through some of the other pieces. So, but I just want to go through that at the beginning of what we do, because it's not, well, it seems daunting. There are many things that we can do with this that can make sense. All right, so I want to start with this idea of kind of where we are. And so originally it was thought that, you go way back into the idea of an atom. It's the smallest thing that can carry that carries the qualities of that element. And they said, no, those are something in there. It's smaller. We have a nucleus. We have electrons, and say, okay, well, we have electrons in this nucleus. The nucleus has protons and neutrons in it. And it was believed for a long time that it was just that was it. And scientists, again, are always asking, well, what's happening? Is there something smaller? Is there something bigger? And so they brought into and said, well, is there something else in there? And they realized that protons and neutrons are built from something called quarks. And protons and neutrons are made up of 3 quarks. There's actually other particles that are similar to protons and neutrons that are made up of other quarks. However, the ones that we experience and the ones that are naturally found here are going to be protons and neutrons. So we have kind of 3 major groups that we work with here. We have force carriers, quarks, and leptons. So force carriers are oh man, it just always kind of blows my mind even just talking about each of these pieces. So force carriers are the particles that allow compatible particles to sense and react to each other's presence through the exchange of these carriers. And so there are particles that are identified that carry the forces between other particles. And we'll talk about those as we get going here. Quarks, they are the heavier, tightly bound particles that make up particles like protons and neutrons. There are 6 different kinds of quarks, and protons and neutrons are made up of in 2 different combinations of those, but there's many other combinations that do exist within the universe, just not ones that we experience on a daily basis. And then leptons are lighter, more loosely bound particles like electrons. So electrons and positrons are both going to fall within that lepton range, and the positron is actually an antiparticle of the electron. Let me go back to that. And then it says an example here: quarks interact via the strong force particles called gluons. Honestly, as we talk about the verbiage of what we're doing here, it just kind of makes me I always wonder how they came up with some of these. And you picture a lab and they're talking and they're like, yeah, we found this thing today, what should we call it? Well, it glues it together. Let's call it gluons. Cool, let's go with it. I don't know. It just kind of makes me laugh with what we have here. When we look at, I'm going to just pull all this up here, and I'll post this online. If it's not already up there, I'll post it sometime today. We have 4 forces that we're going to talk about. The first one, the strongest one, is the strong force, sometimes talked about as the nuclear strong force. And so we'll use that, just pick that as one as the strongest of what we have. That's the force that holds your protons and your neutrons together in the nucleus of the atom. The next strongest is your electromagnetic force. Your electromagnetic force is 1/100th of the strong force, relatively. And so this is the one that we have when we're talking about positives and negatives and dealing with the charge. The next one that we have, oh, hey, I do not want to reinstall Chrome right now. All right, the next one that we have is our weak nuclear force. It has a relative strength of 10 to the -6th. It is found in a lot of the transitions that we have that we'll be talking about in what we're doing. And so it's still a nuclear force, but it's not as strong as a strong force. And we don't see it as often with what we're doing. And then the gravitational force comparatively has relative strength of 10 to the -39th. And so when we talk about, like, just on this range, these are the naturally occurring forces that we experience. So when we talk about the strength of those, comparatively, if the strong force is a 1, gravitational force is 10 to the -39th in strength. And so huge range in the forces that we have available to us. That's 10 to the negative 39th, in case you were wondering. All right, so the idea here is that all forces are due to the exchange of some particles between similar elementary particles. So two protons in space, it was thought of that the protons exchange photons to repel each other because of this exchange. So there's this idea that there's some physical piece to that, just to that interaction that we have that causes the force. So this drives our force particles, and it helps us understand what's happening on a larger scale. The photon exchange, you'll see on the chart that we'll look at that the photon exchange goes along with the electromagnetic force. In the strong force, they talked about only in the nuclear range. Strong force has a particle called the gluon, and it has a very short life. So again, this will make a little bit more sense with what's happening. The photon has a long-lived life. The gluon has a short life, and so those and the drawings that they have on there, those go along with our Feynman diagrams. Come on. So these are the ones that we have, the range. So we have our strong, electromagnetic, weak, and gravitation forces. The range on these it varies depending on what type of force it is. Both electromagnetic force and gravitational force are infinite, and so they're ones that we're able to that like when we calculate them using g times m1 m2 over the radius squared, and then k times q1 q2 over the radius squared, that you can calculate that infinitely. It won't necessarily be measurable infinitely, but it can be calculated infinitely. Strong force and weak force both have a teeny tiny range. The strong force is 10 to the negative 15th meters, and we talked about that. That's what's holding together your protons and neutrons within the nucleus. Your weak force is even smaller than that. It's existing inside of those protons and neutrons. It's teeny tiny, and it's used. Sometimes it ends up being just a transitional force as you're looking at the shift from, like in beta decay, the shift from a proton to a neutron or a neutron to a proton. Talk about quarks here. Get all these up here. So here's the deal. We have talked about protons. And so we've talked about protons, we've talked about neutrons. And so with that, we have, those are ones, we symbolize that with P and with N. But there's other types of particles that we don't talk about because they're not ones that naturally exist right around us. So lambda, omega, we've got different deltas. The symbol next to the delta, so delta 0, delta negative, delta plus plus, delta plus, those that indicates the charge that goes along with it. So you have a neutral delta, negative delta, double positive delta, stuff like that. So these are ones that are available. They're ones that exist, but they're not found around us on a regular basis. Some of them are lab created. Some of them are kind of hypothesized that they would be found in other places in the universe, and some of them are going to be transitional on depending on different interactions. So quarks look like this. We have, if you look at the chart here, you see the letters in the middle. And so you have U, C, T up top, and D, S, and B on the bottom. And the ones in the top row have a charge that indicates that it's 2/3 of an electron. So 2/3 of that 1.6 times 10 to the negative 19th. The ones on the bottom row have a negative third of that. So the charges are as follows. You have up and down. So U and D are up and down. Those are the ones that will make up the protons and the neutrons. And then you have C is charmed, S is strange. And then in that third column, you have top and bottom. I don't know if they ran out of weird names. So they said, this is on top, this is on bottom. We're going to go with that. And they're different families. When we're talking about quarks, the families are not as important. When we talk about leptons, the families become important. And so up and down, charmed, strange, top and bottom. And depending on the combination that you have of those will depend on the overall charge that you have. The last column there says baryon number. All quarks have a baryon number of 1/3. And baryon number is going to have, that's going to be part of what needs to be conserved when we're looking at our conservation laws for atomic reaction or nuclear reactions here. And then it says at the bottom that all quarks have a strangeness number of 0, except the strange quark that has a strangeness number of -1. Again, it'll be something that can be conserved. All the other quarks can kind of work interchangeably in the way that the conservation laws will go, but if you have a strange quark that is present on one side of your nuclear equation, then on the other side, you would have to have that conserved as well. Things to remember here, a proton is up, up, down. So it includes 2 up quarks and a down quark. And a neutron is up, down, down. It includes 1 up quark and 2 down quarks. If you look at the charges of those, you can memorize them, but you can also deduce them from the chart if you need to, because we know that a proton has a +1 charge. So if you have 2 ups, you would have 4/3 of a charge, and 1 down would be -1/3. So 4/3 minus 1/3 would give you 3/3, which would give you 1, a +1. A neutron is an up, down, down. So with the single up, you have a +2/3 charge. And with 2 downs, you would have 2 -2/3, and those cancel out to be 0. And the neutron, the overall charge on a neutron is 0. So these will be 2. If we were taking the exam, it always shows up on one of them in usually in paper 1, where it's like, what is the quark configuration of a proton? And it'll say up, up, down, up, up, down, down. It'll have a few other ones in there, and you just need to know it. So these quarks, when we're talking about the way that they're combined here, you have 3, when you have 3 quarks together, you're able to make different particles. Every particle also has an antiparticle. And so if you have, and usually we'll draw it with a line above it. So, and if you look in the middle, well, first of all, it has the same mass, but all of its quantum numbers are opposite. So if I have an anti, let's say I have, if I go back to the chart that we just had here, let's say I have an anti-up, the charge would be -2/3. If I had an anti-down, the charge would be +1/3. And so, and the baryon number would be negative. If I had an anti-strange, the strangeness number would be +1. There's a lot of rules that we're looking at here. When matter meets antimatter, both will annihilate each other and become energy. Again, super goofy. We're always going to draw the antiparticle with a bar above the top of it, and so, and we'll say it like that. So you might say like P bar or E bar if it's, and the only time that we call it something different with an anti-electron, we can also call that a positron. We have that. There we go. So we would talk about this at the bottom. So we have our chart there for our quarks. If we look at the bottom here, it's talking about the idea of an anti-up quark would be a U bar. And that's just what you say with that. We have some other particles. Or we have some combinations of particles, sorry. So overall, we have something called a hadron. A hadron is a particle that participates in the strong force. So if it's dealing with quarks, it has the potential to be a hadron. We have two different kind of qualifications of that. We have a baryon, which is made up of 3 quarks. So that's like our proton and our neutron. Antibaryon would be made up of 3 antiquarks. Meson is made up of a quark and an antiquark pair. So if you have a pair and one's a quark and one's an antiquark, we classify that as a meson. So since quarks participate in the strong force, and since baryons and mesons are made up of quarks, baryons and mesons are hadrons. One of the things I'm going to have you do this week is to make a sort of a visual representation of how all these pieces go together. And normally what we would do in class is you'd be on the big wooden tables, and I'd give you dry erase markers, and you would like draw out this kind of mind map of how it all works. And that'll be one of the things that you'll do to help make it work here. The idea of quark confinement is basically just that a single quark cannot be isolated. So when we talk about, so this behaves a little bit differently than when we talk about protons, neutrons, and electrons, because we can pull out a proton, a neutron, or an electron on its own. But when we're talking about quarks, they cannot say you can't pull them apart. And so at least at this point in our scientific path, it has been recognized that there's not been a way figured out to pull apart the quarks. And so the quarks do have to come in either in the pair for a meson of the quark antiquark, or as a baryon with a 3 quark figuration. Just talks about the charges. I talked through that a little bit. The proton is a baryon, and it's made up of 2 quarks and a down quark, 2 up quarks and a down quark. So up, up, down. It's a hadron because hadrons participate in the strong force. Neutron is a baryon made up of 1 up quark and 2 down quarks, and it is also a hadron because it's participating in the strong force. The charges are shown there and how they are put together. All right, baryon numbers go along with our conservation laws, and we'll talk about those later. The baryon number of a proton and an antiproton, baryon number of a meson. So you have your proton. If you have a regular proton, all quarks have a baryon number of +1/3. So if you have a regular proton, your baryon number of that proton is a +1. If you have an antiproton, remember that all of the mass is the same, but your nuclear numbers are all the same, are all opposite. And so if you have an antiproton, you have -1/3 for all of them. So an antiproton would have a baryon number of -1. When you have a meson, because you have a quark and an antiquark combination, the quark has a +1/3, the antiquark has a -1/3, and so a meson will always have a baryon number of 0. And so the baryon number will be conserved in our reactions, and we'll talk about that later. Okay, I want to get through. Strangeness is just if it has a strange in there. If it doesn't have a strange in there, you don't have to think about strangeness at all. If it has a strange in there, strangeness has to be conserved from one side of the nuclear equation to the other. And that only happens with the strange particles. And sometimes it gets extra goofy when you're doing that because there's just lots of weird stuff that goes along with it. That's just an example. I'm going to jump through this. You guys, it's already 9 o'clock. My goodness. Oh, goodness gracious. All right, let's talk about this a little bit, and then I'm going to wrap up. Quark confinement means we cannot separate single quark. We talked about that. The nature of the strong force holds them together. And so in order to do that, we would need to provide energy that's proportional to the separation, which is huge. And so automatically there's going to be something else that'll form as opposed to having it be isolated. Let's see. All right, I'm going to just show you this real quick. Leptons are where we have our electrons. So we experience electrons and we experience neutrinos. We've talked about the idea of electrons and antineutrinos when we're dealing with beta decay. And so the same thing happens here, where in the first column, in the first family here, we experience electrons because it's what's found naturally around us. But then we also have mu and tau. So muons and then tau are ones that we can also, that can exist and do exist. They're just not in mass around us. And so leptons have antiparticles as well. And so leptons do not react to the gluon or the strong force. They don't experience the strong force. The strong force is only in the nucleus of the atom. They do interact with the photon, the electromagnetic force carrier. Quarks react both to the gluon and the photon, but leptons only to the photon. And then the leptons, the 6 leptons that exist, we have our electron neutrino, our muon neutrino, and our tau neutrino. And then we have our electron, muon, and tau. So those are the 6 that go together. The electron neutrino sticks with the electron, the muon neutrino sticks with the muon, and the tau neutrino sticks with the tau. So you can't have an electron with a muon neutrino. So we will specify those as we go along. Leptons and quarks also react to gravitons because gravity goes along with anything that has mass. All right, so here's what I'm going to do. That's a ton of stuff. I hope your brain is a little bit jostled, just with the terminology and the different pieces we're doing. With the amount of time we have and with the different stuff that we have going on here, this is going to take us more than just the week that we have. So what I'm going to do is I'm going to take the assignment and I'm going to break it up. The assignment I'm going to give you for right now is just looking at making some sense of the different pieces we talked about. So looking at the force carriers, looking at the quarks, and looking at the leptons, making some sense of that. When we meet on Tuesday, I'm going to talk about the conservation laws that go along with that. So the probability that something within that can exist. And so when you see an equation and you see the different pieces of that, then you can recognize what's happening there. The next Thursday, I'm going to take, and we'll talk about Feynman diagrams and looking at the way to visually represent what's happening with these. And then that next week, we'll wrap all of this up. So we're going to spend 2 weeks on this. I like to spend 2 weeks on it. It just sometimes gets caught up because we're making a push toward the end of the year to make sure that we have time to review. So what that means is you'll have a lot less work to do for next week, which works lovely because you should be wrapping up your IAs and submitting those. So I hope, like I said, I hope your brain is fully and completely jostled. I'll have some videos up there that you can watch and sort of make a little bit more sense of this. And then hopefully the work that I have you doing this week, you'll be able to break it apart and work through the different pieces and make some sense of it. So I hope you're having a great week. Enjoy this awesome weather. This weekend's supposed to get like around 50. Cannot wait. And we'll see you next week. Thanks. I'll stay on if you have any questions. We'll see you later.